Welcome to this presentation on Dalton's law of partial pressures. Have you ever wondered what determines the total pressure when different gases mix together? Whether we are talking about the air you breathe, the bubbles escaping from a freshly opened soda, or the carefully blended breathing gas inside a scuba tank, the answer lies in one elegant law, first observed in 1801. Dalton's law of partial pressures states that the total pressure of a gas mixture equals the sum of the individual pressures each gas would exert if it alone occupied the container. This single principle governs atmospheric science, respiratory physiology, industrial chemistry, and the safety of divers exploring the deep ocean. In this presentation, we will explore the law's meaning, its molecular basis, its many applications, and the problem-solving skills you need to apply it confidently. Meet John Dalton, the self-taught English scientist who gave us this law. Born in 1766 in Eaglesfield, Cumberland, into a humble Quaker family, Dalton received little formal education but taught himself mathematics, meteorology, and chemistry. He kept a daily weather journal for 57 consecutive years, recording more than 200,000 individual observations. He was the first to describe color blindness in detail, a condition still called Daltonism in his honor. While studying the behavior of water vapor in air during 1801, Dalton noticed a remarkable regularity. The total pressure of a gas mixture depended only on the amount of each gas present, not on their chemical identities. He published this empirical law in 1802 in the Memoirs of the Literary and Philosophical Society of Manchester. So, what exactly is partial pressure? Imagine a sealed container holding a mixture of two different gases, perhaps oxygen and nitrogen. The partial pressure of each gas is defined as the pressure that gas would exert if it alone occupied the entire volume of the container at the same temperature. It is a notional or hypothetical quantity, but it is enormously useful. Even though both gases share the same space and collide with the same walls, the oxygen molecules behave as if the nitrogen were not there, contributing their own independent pressure. The nitrogen molecules do the same. The total pressure you measure is simply the sum of these independent contributions. This independence of gas contributions is the conceptual heart of Dalton's law. Here is the master equation. The total pressure exerted by a mixture of non-reacting gases equals the arithmetic sum of the partial pressures of the individual gases. Mathematically, P total equals P1 plus P2 plus P3, and so on, summed over all n components of the mixture. Each partial pressure, P sub I, represents the pressure contributed by the ith gas. The law is empirical, meaning Dalton discovered it through careful measurement of gas mixtures, but it emerges naturally from the kinetic molecular theory of gases. That theory tells us that ideal gas molecules are so far apart that they do not interact with each other except through elastic collisions with the container walls. The Dalton's law equation appears at the top right of the slide for your reference. One of the most useful forms of Dalton's law connects partial pressure to the mole fraction of each component. The mole fraction, x sub I, is simply the number of moles of gas I divided by the total number of moles in the mixture. Because partial pressure is directly proportional to the number of molecules present, we can write a beautifully simple relationship. P sub I equals x sub I times P total. This means that if you know the mole fraction and the total pressure, you can immediately find the partial pressure of any component. For example, dry air contains about 21% oxygen by volume, so the mole fraction of oxygen is 0.21. At a total pressure of 1 atmosphere, the partial pressure of oxygen is exactly 0.21 atmospheres. Why does Dalton's law work so well? The answer lies in the fundamental assumptions of the kinetic molecular theory of gases. In an ideal gas, molecules are extremely far apart compared to their own size. The distance between molecules is typically 10 times greater than the molecular diameter, so molecules spend most of their time in free flight between collisions. They do not exert forces on each other except during brief elastic collisions. Because molecule A does not know molecule B is there, the pressure contribution from molecule A is exactly the same whether molecule B is present or not. Each gas independently collides with the walls and exerts its own pressure. The total pressure is simply the sum of these independent pressure contributions. This is why Dalton's law is exact for ideal gases and nearly exact for real gases at low pressure and high temperature. Real gases do not follow Dalton's law perfectly under all conditions. Deviations become significant at very high pressures and at temperatures close to the condensation point. At high pressure, molecules are squeezed close together, and the physical volume occupied by the molecules themselves becomes a significant fraction of the container volume. The free space available for molecular motion is reduced, so the gas exerts a different pressure than an ideal gas would. At low temperatures, molecules move slowly enough that attractive intermolecular forces between them can pull them slightly closer, reducing the measured pressure. These deviations are captured by more sophisticated equations of state, such as the van der Waals equation. However, for most practical chemistry problems at pressures below a few atmospheres and temperatures well above the boiling point, Dalton's law remains highly accurate. The most familiar gas mixture is Earth's atmosphere. Dry air is composed of about 78.1% nitrogen, 20.9% oxygen, 0.93% argon, 0.04% carbon dioxide, and trace amounts of neon, helium, methane, and other gases. At sea level, the total atmospheric pressure averages 1.00 atmosphere, or 760 millimeters of mercury. Using Dalton's law, we can immediately calculate the partial pressure of each component. Nitrogen contributes 0.781 atmosphere, oxygen contributes 0.209 atmosphere, argon contributes 0.0093 atmosphere, and carbon dioxide contributes 0.0004 atmosphere. This is why partial pressure is essential to respiratory physiology. At high altitude, although the percentage of oxygen in the air is unchanged, its partial pressure drops along with the total atmospheric pressure, leading to altitude sickness. A classic application of Dalton's law appears in laboratory gas collection. When a gas is produced by a chemical reaction and bubbled through water, the gas becomes mixed with water vapor. The total pressure measured in the collection vessel is the sum of the partial pressure of the dry gas you want to collect, plus the partial pressure of water vapor. To find the actual amount of dry gas produced, you subtract the water vapor pressure, which depends only on the temperature, from the total pressure. At 25 degrees Celsius, the vapor pressure of water is 23.8 millimeters of mercury. At 30 degrees Celsius, the vapor pressure is 31.8 millimeters. This elegant technique, developed by early 19th century chemists, remains a standard procedure in chemistry labs worldwide. It demonstrates Dalton's law in action, allowing us to isolate and measure the amount of a gas even when it is mixed with water vapor. Perhaps the most dramatic real-world application of Dalton's law is in scuba diving and respiratory medicine. As a diver descends below the surface, the total pressure increases by about 1 atmosphere for every 10 meters of seawater. At 30 meters, the total pressure is 4 atmospheres. But the proportions of oxygen and nitrogen in the breathing gas remain constant, so their partial pressures quadruple. The partial pressure of oxygen at 30 meters is 0.84 atmospheres, which exceeds safe limits and risks oxygen toxicity, potentially causing seizures. The partial pressure of nitrogen also rises dangerously, causing nitrogen narcosis, often called the rapture of the deep. To avoid these dangers, divers use specialized gas mixtures like nitrox, trimix, or heliox, carefully calculated using Dalton's law to keep each partial pressure within safe physiological limits. Test your understanding. Here is your first question. A container holds a mixture of 3 gases with partial pressures of 0.40 atmospheres, 0.80 atmospheres, and 0.30 atmospheres. What is the total pressure of the mixture? Take a moment to consider. The 4 options are A. 0.90 atmospheres, B. 1.20 atmospheres, C. 1.50 atmospheres, or D. 2.00 atmospheres. Pause and think about your answer. The correct answer is C. 1.50 atmospheres. Apply Dalton's law by simply adding all the partial pressures together. 0.40 plus 0.80 plus 0.30 equals 1.50 atmospheres. Option A is the sum of only two pressures. Option B skips the smallest component, and option D is an incorrect overestimate. The core of Dalton's law is the simple additive nature of partial pressures for non-reacting gases. Here is question 2. A gas mixture contains 4.0 moles of nitrogen and 1.0 mole of oxygen. If the total pressure is 2.5 atmospheres, what is the partial pressure of oxygen? The four options are A. 0.50 atmospheres, B. 1.00 atmosphere, C. 1.50 atmospheres, or D. 2.00 atmospheres. Take a moment to think. The correct answer is 0.50 atmospheres. First, find the mole fraction of oxygen. The mole fraction is 1.0 divided by 5.0, which equals 0.20. Then, the partial pressure of oxygen is 0.20 times 2.5 atmospheres, which equals 0.50 atmospheres. Option B would be the answer if you used the mole fraction of nitrogen instead. Option C is incorrect arithmetic. Option D is the total pressure multiplied incorrectly. The mole fraction connection is the most useful form of Dalton's law. Question 3. A chemist collects oxygen gas over water at 25 degrees Celsius. The total pressure in the collection vessel is 745 millimeters of mercury. The vapor pressure of water at 25 degrees Celsius is 24 millimeters of mercury. What is the partial pressure of oxygen? The four options are A. 24 millimeter of mercury, B. 721 millimeter of mercury, C. 745 millimeter of mercury, or D. 769 millimeter of mercury. Pause and consider. The correct answer is B. 721 millimeters of mercury. Apply Dalton's law. The total pressure equals the partial pressure of oxygen plus the partial pressure of water vapor. Solving for the partial pressure of oxygen gives 745 minus 24, which equals 721 millimeters of mercury. Option A is just the water vapor pressure. Option C is the total pressure, ignoring water vapor. Option D incorrectly adds the two pressures. Subtracting the water vapor pressure is the key Dalton's law step for gases collected over water. Question 4. Atmospheric pressure at the summit of a high mountain is 0.60 atmospheres. Assuming the composition of air is unchanged, what is the partial pressure of oxygen at this altitude? The four options are A. 0.126 atmospheres, B. 0.21 atmospheres, C. 0.40 atmospheres, or D. 0.60 atmospheres. Take a moment to think. The correct answer is A. 0.126 atmospheres. The mole fraction of oxygen in air is 0.21. Multiply by the total pressure to get 0.21 times 0.60 atmospheres, which equals 0.126 atmospheres. Option B is the mole fraction, not a pressure. Option C is incorrect arithmetic. Option D is the total pressure, not the partial pressure. This problem illustrates why high-altitude breathing is difficult. The percentage of oxygen stays at 21%, but its partial pressure drops with the total pressure. Question 5. A diver is at a depth where the total pressure is 3.0 atmospheres. The breathing gas is 30% oxygen and 70% nitrogen. What is the partial pressure of nitrogen? The four options are A. 0.7 atmospheres, B. 2.1 atmospheres, C. 0.9 atmospheres, or D. 3.0 atmospheres. Take a moment to think carefully. The correct answer is B. 2.1 atmospheres. The mole fraction of nitrogen is 0.70. The partial pressure of nitrogen is 0.70 times 3.0 atmospheres, which equals 2.1 atmospheres. Option A is the surface partial pressure of nitrogen, not at depth. Option C is the partial pressure of oxygen at this depth. Option D is the total pressure itself. At 3 atmospheres, the partial pressure of nitrogen at 2.1 atmospheres is high enough to cause significant nitrogen narcosis, which is why technical divers use trimix or other special gases below about 30 meters. Problem 1. A container holds a mixture of helium and neon. The partial pressure of helium is 0.60 atmospheres, and the partial pressure of neon is 0.40 atmospheres. What is the total pressure inside the container? We will solve this step by step. Step 1. Identify the given partial pressures. We have P helium equals 0.60 atmospheres and P neon equals 0.40 atmospheres. We need to find the total pressure. Step 2. Apply Dalton's law of partial pressures. P total equals P helium plus P neon. The pressures simply add because no chemical interaction occurs between the noble gases. Step 3. Substitute and calculate. P total equals 0.60 plus 0.40, which equals 1.00 atmospheres. The mixture reaches standard atmospheric pressure. The check. Dalton's law requires non-reacting gases. Helium and neon are both noble gases with full valence shells, so they do not react, and Dalton's law applies exactly. The final answer is 1.00 atmosphere of total pressure. Problem 2. A gas mixture is prepared by combining 2.0 moles of methane and 3.0 moles of ethane. The total pressure of the mixture is 5.0 atmospheres. What is the partial pressure of methane? Let's work through this step by step. Step 1. Find the total number of moles. The total moles equal 2.0 plus 3.0, which equals 5.0 moles. Both gases are non-reacting hydrocarbons at typical conditions. Step 2. Calculate the mole fraction of methane. The mole fraction of methane is 2.0 divided by 5.0, which equals 0.40. As a sanity check, the sum of mole fractions is 0.40 plus 0.60, which equals 1.00. Step 3. Apply Dalton's law to get the partial pressure. The partial pressure of methane equals 0.40 times 5.0 atmospheres, which equals 2.0 atmospheres. This result beautifully matches the mole ratio of 2 to 3 because partial pressure is directly proportional to mole fraction. For comparison, the partial pressure of ethane is 0.60 times 5.0, which equals 3.0 atmospheres. The final answer is 2.0 atmospheres of partial pressure for methane. Problem 3. Hydrogen gas is collected over water at 22 degrees Celsius. The barometric pressure is 758 millimeters of mercury, and the vapor pressure of water at 22 degrees Celsius is 20 millimeters of mercury. The gas occupies 250 milliliters. What volume would the dry hydrogen occupy at STP, which is 0 degrees Celsius and 760 millimeters of mercury? We will solve this in 4 steps. Step 1. Apply Dalton's law to find the partial pressure of hydrogen. P total equals P hydrogen plus P water vapor. Solving for P hydrogen gives 758 minus 20, which equals 738 millimeters of mercury. Step 2. Convert to atmospheres for easier handling. The pressure is 738 divided by 760, which equals 0.971 atmospheres. The temperature is 22 plus 273, which equals 295 Kelvin. Step 3. Set up the combined gas law for the new conditions. At STP, the pressure is 1.00 atmosphere and the temperature is 273 Kelvin. The new volume is P1 times V1 times T2 divided by T1 times P2, which is 0.971 times 250 times 273 divided by 295 times 1.00. Step 4. Calculate the final volume. The numerator is 0.971 times 250 times 273, which equals 66,266. Dividing by 295 gives 224.6 milliliters. Rounded to 3 significant figures, the final volume is 225 milliliters at STP. The Dalton step of subtracting water vapor was essential to the solution. Problem 4. A 5.0-liter container holds a mixture of nitrogen, oxygen, and carbon dioxide. The partial pressure of nitrogen is 1.2 atmospheres, the partial pressure of oxygen is 0.5 atmospheres, and the total pressure is 2.0 atmospheres. Find the partial pressure of carbon dioxide and its mole fraction. Let's solve this in 4 steps. Step 1. List what is known. P total is 2.0 atmospheres. P nitrogen is 1.2 atmospheres, and P oxygen is 0.5 atmospheres. We want to find P carbon dioxide and its mole fraction. Step 2. Rearrange Dalton's law to solve for the unknown. P carbon dioxide equals P total minus P nitrogen minus P oxygen. Step 3. Substitute the values. P carbon dioxide equals 2.0 minus 1.2 minus 0.5. which equals 0.3 atmospheres. Step 4. Calculate the mole fraction of carbon dioxide. The mole fraction is 0.3 divided by 2.0, which equals 0.15. So 15% of the molecules in the container are carbon dioxide. As a check, 1.2 plus 0.5 plus 0.3 equals 2.0 atmospheres, which matches the total pressure. This technique is widely used in respiratory medicine and industrial gas analysis to determine an unknown component when the others are known. The final answer is P carbon dioxide equals 0.3 atmospheres, and its mole fraction is 0.15. Problem 5. A scuba diver is 20 meters below the ocean surface, where the total pressure is 3.0 atmospheres. The breathing mixture is 32% oxygen and 68% nitrogen. Find the partial pressure of each gas. Is the oxygen partial pressure safe for recreational diving? We will solve this in 4 steps. Step 1. Identify the mole fractions and total pressure. The mole fraction of oxygen is 0.32, the mole fraction of nitrogen is 0.68, and the total pressure is 3.0 atmospheres. As a sanity check, 0.32 plus 0.68 equals 1.00. Step 2. Calculate the partial pressure of oxygen. P oxygen equals 0.32 times 3.0, which equals 0.96 atmospheres. Step 3. Calculate the partial pressure of nitrogen. P nitrogen equals 0.68 times 3.0, which equals 2.04 atmospheres. Step 4. Check oxygen safety. The maximum safe partial pressure of oxygen for recreational diving is 1.4 atmospheres. Since 0.96 is less than 1.4, the partial pressure is safe for the dive duration. The diver can breathe this mixture at 20 meters without oxygen toxicity risk. However, the partial pressure of nitrogen at 2.04 atmospheres is approaching the limit where nitrogen narcosis becomes significant, around 2.2 to 2.4 atmospheres. For deeper dives, technical divers use trimix, a mixture of helium, nitrogen, and oxygen, to reduce the nitrogen partial pressure. The final answer is P oxygen equals 0.96 atmospheres, which is safe, and P nitrogen equals 2.04 atmospheres. Let's review the key concepts of Dalton's law of partial pressures. First, the law itself. The total pressure of a gas mixture equals the sum of the partial pressures of each component. Mathematically, P total equals P1 plus P2 plus P3, and so on. Second, partial pressure is defined as the notional pressure each gas would exert if it alone occupied the container at the same temperature. Third, the mole fraction relationship. P sub I equals X sub I times P total, where X sub I is the mole fraction of component I. Fourth, the law works perfectly for ideal gases and remains highly accurate for real gases at low to moderate pressure and high temperature. Fifth, applications. Atmospheric science, gas collection over water, and respiratory physiology in scuba diving all depend on Dalton's law. Sixth, limitations. Deviations occur at high pressure and low temperature when molecular interactions become significant, and these are captured by the van der Waals equation. Master these concepts, and you have a powerful tool for understanding gas mixtures in chemistry, physics, and engineering. Thank you for joining this presentation.